If we take a strip of nice shiny magnesium and put it into a solution containing copper ions and give it a few minutes, we find that the magnesium gets this kind of fuzzy black stuff growing on it. What's happening is that the magnesium metal is becoming magnesium ions and is dissolving. The copper ions that were in the solution are becoming copper metal and are depositing on the magnesium. And that happens spontaneously. You don't have to do anything to it. If you take a strip of copper metal and put it into a solution of magnesium ions, nothing happens. So this reaction goes from magnesium to magnesium ions. It does not go in the reverse direction. How do we know which direction it goes in? We have an activity series. This lists metal in order of decreasing tendency to lose electrons. When a metal undergoes a reaction, it loses electrons. So the activity series, and I've talked about metals as being masculine, right? So the metals are guys, and the activity series is this list of guys in order of hotness. Okay, so the hottest, most active, most reactive guys are at the top, and the ones that just don't do much of anything are at the bottom. And so in terms of how do these metals get together with nonmetals, this activity series predicts who's going to have a reaction and who's not. So metals at the top of the list are most easily oxidized. They're the most reactive. The ones at the bottom are the least reactive. And so here is a partial activity series. This isn't including all of the metals. What's listed here are half reactions. So this reaction, lithium metal going to lithium ion and losing an electron, that cannot happen by itself because there's got to be something else to take the electron. This won't happen by itself. It's half of a reaction. Doesn't really matter what the other half is, though, and so that's why we leave it off. These reactions are most likely to occur in the forward direction. Half reactions at the bottom are not likely to occur in the forward direction. I don't know what's up with my pointer. I can't point at the bottom line. Are most likely to occur in the reverse direction. So if you take, like we were looking at magnesium and copper. So magnesium is more active than copper because he's higher on the list. So magnesium will react in this forward direction. It'll become oxidized. And copper will react in the reverse direction. So let's stick an anion in there. Let's just use chloride. So if we've got magnesium metal reacting with copper chloride, that's aqueous. Now we talked about predicting reactions. We talked about this is a guy and this is a girl, and they're going to swap partners, right? So magnesium comes to the party all by himself, but he's cooler. He's more macho than copper, and so he's going to leave with the girl, and copper's going to go home alone. That's how this list works. Lithium is most likely to get the girl, and gold is least likely. So when we swap the partners, we're going to get copper metal and magnesium chloride. That would be aqueous. So the two half reactions that are occurring there are magnesium going to magnesium ion, and it's going to lose 2 electrons when it does that. And copper 2+ will gain 2 electrons and become copper metal. So this reaction is going reverse of how it's written in this list, and magnesium is going forward. So if you have a metal reacting with an ionic compound, like this one, you look at the ion that's part of the compound and see where does it fall on the activity list. If it's below this one's going to steal the anion. It's going to steal the girl. Any questions? Yes?
Will we be given this table or test?
You will be given an activity series. It might be a much smaller activity series, but you'll be given whatever it is that you need. Yeah, don't memorize the activity series. Hydrogen is in here because H plus is what's released by acids, or H3O plus, and some metals will dissolve in acid. And so hydrogen is in here. Hydrogen is a non-metal, but acts like a metal sometimes. It's very conflicted and confused. It's the little brother, little sister gets away with everything. Gold is very low on the activity series. It's at the bottom of the one that was listed there. It does not oxidize easily. It's difficult to oxidize. And so gold resists tarnishing, and that's what makes it real popular as, for jewelry, because it doesn't get all tarnished. Silver does tarnish, but it is also down here on the list. And you might say, well, silver tarnishes, it gets so nasty I have to keep polishing the silver. Yeah, but it's not reactive like sodium. Sodium reacts with water in the air, right? But you can take a silver spoon and put it in water and nothing happens. So it's much less reactive than these guys up here. These guys are like crazy reactive. Okay, so determine whether each redox reaction is spontaneous, meaning it will happen in the direction that it's written in. And here is this list. Okay? So again, think of this as a list of guys, maybe at your high school, the girls got together and kind of ranked the guys. And guys probably do that too, but that doesn't have a correlation in chemistry. So here we've got zinc and nickel ion. So what we want to do is say, well, find out who's higher on the list. So we go over here. Here's zinc, and here's nickel. So who's the cooler guy, zinc or nickel? Zinc. Zinc's higher on the list. That says that zinc is going to react, zinc is going to become an ion. So in this reaction, we've got zinc becoming an ion, and nickel was an ion, and it's becoming an atom again. If there was a girl involved here, let's say it's oxide. Oxide would come in with the nickel, right? And it would leave with the zinc.
So it's spontaneous?
This is spontaneous. Zinc will react with nickel ion.
I don't see how you got that.
Okay. So here's zinc. No charge. That means he's coming to the party by himself. And here's nickel. Now in the equation it doesn't show who his date is, but because he's got a 2+ charge, that means he's got a date. Okay, so they come to the party and they mix and they mingle, and we know from this list over here that zinc is a more desirable guy than nickel. So zinc is going to steal the girl and nickel's going to go home by himself.
How is that made? Why is that?
Well, zinc will steal nickel's girl, so this will happen. If we look at this reaction, zinc and calcium, we have to find them on the list. Here's zinc and here's calcium. Who's cooler, zinc or calcium? Calcium. So here we've got zinc coming alone again, and calcium's got the girl. Is zinc going to be able to steal calcium's girl? No. It's like, I'm with calcium, he's cooler than you, I'm not leaving with zinc. He's no fun. So we can write this reaction, but it's not going to happen. This is not going to happen. The reverse would happen. If calcium came alone and zinc had the girl, calcium's cooler. I used to say this as the list of "Quién es muy más macho?" But that's a Saturday Night Live skit that you guys are too young to have seen. It's a bummer, because muy más macho, I don't know, it's just fun to say. Calcium is, I got to come up with something else that's more appropriate for this generation. But calcium's more macho than zinc, and so calcium would steal the girl. So we can't have zinc stealing the girl from calcium, because it's just not going to happen. He can't do it.
You can say calcium is a mandingo.
A mandingo? I'll have to Google that.
It's like Papa Jingo.
That doesn't help.
The bigger guy always wins.
Yeah, so I'll be taking suggestions for what I can say. I've got mandingo. I'm open to other suggestions. We can predict if a metal will dissolve in acid by comparing it to hydrogen in the activity series. So metals above hydrogen will dissolve in acids, metals below will not. There's one important exception, and that's nitric acid, and I will not try to trick you with this, but nitric acid will dissolve some of the metals that are below hydrogen, and that's because it does it through a different sort of a half reaction. And so we're not going to worry about that. But here we have nitrogen. There's no nitrogen in there. That's zinc. Zinc and hydrogen. This pointer is making me crazy. Can't do it. Zinc and hydrogen. And so we would look at the activity series. Here's hydrogen, and there's zinc. And so what we're envisioning here is that zinc's coming to the party, stag, and hydrogen had the girl because it's got a charge. Seriously, I can't point to hydrogen. Hydrogen has the girl. Because zinc is mandingo, he gets the girl, and the reaction occurs.
It's part of this shoe, you gotta use it.
Okay. Yeah, I gotta look that up. I don't have any context for that one. Okay, so does silver dissolve in hydrobromic acid?
No,
Why?
because it's below it.
Excellent. Okay, no, it doesn't because it's below hydrogen. Silver's down here, it's below hydrogen. So silver, metal, plus hydrobromic acid, that's going to be H+, right? We've got H+ and Br- in here. So the hydrogen has the girl here. Silver is less cool than hydrogen. And so silver cannot take the girl from hydrogen, and this will give us no reaction. Why is hydrogen in bold? I think because it's odd. It's weird. Because this is a diatomic nonmetal in this list of metals. Yeah.
Does the strength of the acid ever make a difference?
By strength, you mean strong or weak acid? No, it doesn't. Because even a weak acid will produce some hydrogen ions. And so something like iron will dissolve in a weak acid or a strong acid. Now, concentration and acid strength could affect how fast it dissolves. If you have a weak acid and a strong acid of equal concentrations, it'll dissolve faster in the strong acid because the hydrogen ion concentration will be greater. But we just need to know, will it dissolve or not?